Okay, welcome to Intro to Photonics. So there's been cause for much celebration lately, and you guys should feel proud to be part of this celebration because the Nobel Prize for Physics was announced yesterday, and it's once again optics that's ruling the world, so to say. I just pulled out the statistic, just going back and looking at all the Nobel Prizes that have been awarded recently. Since 2000, 20 Nobel Prizes have been awarded to optics related work. And so we are continuing that trend. Of course, you say 18 years, 20 Nobel Prize, how does that work? It's not always in physics, right? Physics, of course, has got the most number of those prizes, but there's also been contributions in chemistry, I think 3 or 4 times chemistry, and also biomedical imaging related work. There was some Nobel Prize given for STED microscopy to get a really less than 100 nanometers sort of resolution in your imaging. There was a Nobel Prize given for that. So overall, it gives you a little more motivation probably to read about this, because as you can see, this is all leading up to something really good, and I'm sure more and more work in optics is going to get recognized as we go on, because it's certainly changing the world around us, right? It's enabling us to do things which we had not dared to dream of before. So I just thought I'll take a few minutes to first of all talk about this particular work that got the recognition Nobel Prize. There are actually 2 aspects to it. One was about cell manipulation, and then the other part was about chirp pulse amplification. Cell manipulation I don't want to talk about right now because it's off from what we had been discussing lately, but chirp pulse amplification, right, is certainly something that it's very much related to what we have been talking about. So let's talk about chirp pulse amplification. Chirp pulse amplification, as the Nobel correctly recognized, is something that was initially demonstrated by Gerard Moreau and Donna Strickland, right? Gerard Moreau was actually a faculty, is a director of the Center for Ultrafast Lasers at University of Michigan at Ann Arbor. So he is the professor, and Donna Strickland was his PhD student. And Donna was actually looking at how to increase the peak pulse energy of light. So essentially what she is looking at is, I have a small pulse like this, right? Let's say it's a picosecond pulse or maybe even a femtosecond pulse. How can I get a large pulse like this? So this is as a function of time, right? How can I get a much larger pulse like this? So I can essentially say the level at this is nanojoules, and the level at this is millijoules. Okay. So how do I achieve this sort of amplification of pulse? Now, if you want to visualize this, what does a pulse consist of? A huge number of photons, right? So you would basically say the pulse energy divided by h nu, that actually gives the number of photons that are packed within this pulse, right? So even when you look at energy, so let's say it's about 1 micron. Actually, the experiments they did was around 1 micron. So, corresponds to about 1.24 eV, right. So, 1.24 multiplied by 1.6 into 10 power minus 19 will give you the corresponding joules, right. So, you say 1 nanojoule is already packing something like a billion photons. Okay. So, you have a billion photons to start with already within this pulse, within a picosecond of duration. And you can imagine when we are talking about amplifier, what was the lifetime that we were talking about? Lifetime of these energy levels, milliseconds, right. So, picoseconds is a very, very small fraction of that. Okay. So, we are talking about starting with a billion photons within a picosecond, and now you want to go a billion times more, or in this case a million times extra, 10 power 6 extra photons, all needs to be packed within that picosecond time scale. So, what is the advantage of that? Of course, when you say you have so many photons going together and let us say it is interacting with a material, okay. Normally your energy level corresponding to this in terms of energy would be something like this, right. So, one photon has an energy h nu, right. But if you have billions of photons all focused onto a same spot in a material, okay, it can interact with the material such that many of these photons add up, they all come to the material at the same time. So, h nu can add up, and you can get effectively the energy corresponding to a very high energy photon. So, what am I talking about? If I am saying 1 micron wavelength, that corresponds to 1.24 eV of energy, right. But if I have 5 of those photons come together at the same time, right, instantaneously, then I have 6 eV, energy corresponding to 6 eV. Energy corresponding to 6 eV in this case would be 0.2 micron wavelength. Okay, it's corresponding to the energy of a ultraviolet photon, or you can even go beyond that and you can actually get the energy corresponding to X-rays by having multiple photons come together at the same point, at the same time. Okay. So, when you go to very high levels of energy within a very short duration, you can actually have this high energy physics, this whole realm of high energy physics becomes, it's within your reach, right. So, you can actually look at interactions, you can break bonds, very high strength bonds. You talk about diamond, right, it's one of the hardest materials that known to us, right. The bond energy, why is it hard? Because the bond energy is very hard, right. So, you need to have a bond energy corresponding to that or higher than that to break that bond. If you break that bond, then you can chisel away diamond, you can shape your diamond, you can cut your diamond, you can polish your diamond, right. So, that is talking about the hardest material that is known to us. Now, every other material is child's play relatively, right. So, you can talk about material processing at a much different scale. You can talk about depositing energy that can essentially allow formation of bonds also. You can break bonds and you can reform bonds. You can do chemical reactions that have never been thought about before. Okay. So, a lot of those things are enabled by having a way of reaching this sort of energy levels within a very short thing. So, how short? We are talking about picosecond or even lower than that. So, question is LASIK treatment in the eye, would it be similar? Yeah, you can say that. Essentially, to do a LASIK treatment, you need to chisel away your cornea, you need to shape your cornea, you need to ablate that. Now, you do not necessarily need millijoules for that, even microjoule level is probably good enough, but that is still a challenge, to get microjoules and within a very short pulse, they use 100 femtosecond pulses in those cases, and that is still a challenge, okay. So, to do this, what exactly is the limiting factor? Well, we go back and look at this picture, right, that we studied upon, right, gain saturation. So, you say you are trying to get an inversion, right. So, you are trying to get an inversion between two energy levels. Right. So, you want such that you want a lot of ions sitting there compared to here, okay, and you're targeting these transitions so you are coming in and stimulating with a photon and you're trying to get a gain from this material. So, that gain will be proportional to the inversion, that is what we've been studying over here, right. But we also realize that as you go more and more number of photons, the first few photons that enter the system will see a huge gain, but then it depletes the gain instantaneously, depletes the inversion instantaneously, and it's going to take some time for it to go back to that, to refill that excited state. And within that time, all the other subsequent photons coming in are seeing lesser and lesser inversion. Okay. So, you essentially see saturation, the gain saturation happening within that amplifier, which limits the amplification that you can get. Okay. So, if you take a picosecond pulse with nanojoule energy, you send it through amplifiers, it so happens you cannot get all that amplification in one go. You can actually have multiple amplifiers, and from nanojoule you can go to 10 nanojoules, 10 nanojoules to 100 nanojoules, and 100 nanojoules to a microjoule. When you are trying to get to that, you are starting to face some serious inversion issues, this gain saturation issues, because now you are trying to amplify several hundred billions of photons together, right. And now you do not have so much inversion that you can provide the same gain for all those photons. So, your gain essentially gets limited, you are not going to be able to amplify beyond a microjoule. So, what did these people come up with? So, yes, let me just erase this for a minute. So, we are talking about having you sending it through one amplifier, right. You get, let us say, 10 dB amplification there, and then you send it through another amplifier, another 10 dB amplification, and then you go beyond that, you hit a stop because of gain saturation. You are not going to be able to amplify beyond that. So, what did they do? They actually came up with a way of chirping the pulse. So, what does chirping the pulse mean? instead of a small pulse, instead of a narrow pulse like this, you actually have a broader pulse. Okay, so broader in terms of time. Okay, and you made it such that the red color is over here, the blue color is over here, and all the other colors are in between. Okay, so you essentially you broaden the pulse, but you broaden the pulse such that you are essentially dispersing the pulse. Remember, we talked about dispersion several weeks ago. I want to go back and see if we can pull up that that particular discussion we had. Lecture 3 maybe. Yeah, bingo. We were talking about dispersion in a prism, right? So what is the basis for dispersion? Different frequencies travel at different velocities because the response of the medium is different, right? The refractive index posed by the medium for different colors is different, right? So you can essentially use something like this, something like the dispersion, to spread out the pulse, okay, and spread out the pulse in time. So what's the advantage of that? Now what I can do is essentially at this point I have the red wavelength, and that's a relatively smaller amplitude pulse, right? And then I go to the orange wavelength, then I go to the yellow and so on, and then I come to the blue wavelength, and it's a relatively smaller pulse. One large pulse like that I've basically flattened out, I chirped it, so it's actually smaller. Each of those colors have smaller magnitude, and not only that, they're all spread out in time. Okay, so now first the red goes in, gets amplified, and before the orange goes in, you have given some time for it to recover, the gain, the inversion to recover, right? And then the orange gets amplified, and before the next color comes in, you're once again giving time for the gain, for the system to recover, and so on. So I'm actually making it look like it's discrete, but in reality this is all continuous, and these are not as broad as red, yellow, orange and all that. These are just different shades of a color, okay, in reality. But you're chirping the spectrum such that, and you're spreading them in time such that these different colors essentially get amplified at slightly delayed time, and that delay is enough for the gain to recover, the atomic system to recover, so that you can provide gain. You're essentially, what you're doing is, in this picture, we are actually at this level. With an individual pulse, you are at this level, right? With a very narrow pulse, you are at this level. But now when I've taken the same energy and I've stretched it out, okay, each of those constituent colors are somewhere at this level. You have removed it from saturation, and so now you are able to achieve more gain. Okay, so with that, I'm able to go through, and I'll go through another amplifier, and what I will do is I will actually go through amplification like this, right, I will get a much larger pulse. But once again, in this pulse also the red is somewhere over here, the color sequence I am maintaining, right. And finally, I go through, in fact, there is a paper in 1985, Optics Communications, okay. So, Donna is the first author, Gerard is the second author. So, it talks about compression of chirped pulses, okay, and that essentially is talking about once it gets amplified like this, it talks about going into a compressor, right, which is actually like a dispersion compensating element, like a grating. Remember, that is what we talked about when we were discussing here, that same dispersing element, we can turn it around and we can actually compensate for that dispersion. And we said this is one way of doing dispersion compensation. We said this multiple slits or grating is another way of doing a dispersion compensation. And a grating type dispersion compensator is preferred over here, because when you are compressing it back, you are actually having so much energy. Remember, I talked about with so much energy you can ablate material. So, if you propagate this pulse or you try to compress this pulse in some optical fiber, let us say, you will end up burning the optical fiber because you have so much energy that is going to ablate that material, and so the entire material will be destroyed, right. Whereas, if you actually have a grating, reflective type grating, yes, of course, there is still this possibility that the pulse can hit the reflection coating and it can end up ablating the coating also. So, what you have to do is take that beam and actually expand the beam. So, the power density that is hitting on that grating is lesser. Instead of a narrow beam going in, you expand it to this size of beam, okay. So, the number of photons per unit area is lesser. So, you do not have the possibility of ablation in that case, right. But you essentially have to go through that, go through a grating which essentially delays the red with respect to the blue and recompresses the pulse to the original form. So, you are taking all this photons that are scattered in frequency and scattered in time, and you are compressing them back to achieve this original pulse shape itself, okay. So, I know there are a couple of questions. So, one is this process which we are calling as chirping, and this process is amplification, and this process is compression. So, this is chirp pulse amplification. They left out compression, but compression is an essential part in it to put everything back and get that large pulse. I know there are a couple of questions. You raised your hand first. So, chirping is actually separating out the frequencies. So, you're separating out the frequencies in time. So, it's basically, you can look at it as negative dispersion. If you thought dispersion is spreading in time, but spreading in time meant that blue was traveling faster than red. This is the negative dispersion. Red is traveling faster than blue. You know, it's that sort of a thing, but both of them end up spreading in time. So, one is negative slope like this, and other is positive slope like this. So, it compensates the two. Yes. No, it cannot create new frequency. Well, if you have a nonlinear material coming into the picture, it can create new frequencies also, right? But you can do that also. But in this case, normally you are just trying to stretch the pulse. You try to keep the frequency content and, huh? Yes, exactly. So, so what we are talking about is a picosecond pulse, which is already a few nanometers wide. So it has got a wide range of frequencies, and that you are, yeah, stretching out further. Okay. So, so this is what they got part of the Nobel Prize for, which is by itself a huge achievement. And since then, for those of you that are interested, there is actually a femtosecond laser lab in our campus, right? So Mano here is actually working in that lab, so he uses that laser on a daily basis, and that laser uses this technique, Chirped amplification technique. It's a commercial laser, right? It's sold for several $100,000, but it's capable of putting out 6 millijoules. 6 millijoules with 100 femtosecond pulses. What, or at least the vendor, when they sold it to us, told us that this is the highest energy laser in India as one system, right? I think people at RRCAT, Raja, RR, what does it stand for? Rajaram, something. Center for Advanced Technologies, RRCAT in Indore, they deal with a lot of these high power lasers, and they do Chirped amplification also. So they might actually contest whether, but what they meant was that this is the highest energy commercial system that's available in India. Okay, but you can go and see that it's of course not see it, but but yeah, see how the laser is working, right? So and we do try to ablate diamond, artificial diamond. Don't think we are storing diamonds there. Artificial diamond. We try to ablate using those lasers, and thanks to these guys for enabling the technology. So yeah, so we are before chirping, you are at about microjoule level, and you can go through several stages of amplification, and you can get to the millijoule level. 2 or 3 stages of amplification you typically need to do. So the minimum pulse width, well, you cannot say it's a minimum pulse width. It's like if you take a nanosecond pulse, you can go up to millijoules, okay, without Chirped amplification. If you take a picosecond pulse, you can go up to, microjoules before you need Chirped amplification. If you take a femtosecond pulse, 1 femtosecond pulse, you are limited to nanojoules. Right. It's basically the total energy that you can get out of the amplifier system, right? For a unit pulse width, that's limited. So you're essentially overcoming gain saturation issues involved with ultra short pulses through this Chirped amplification technique. Make sense? You would have thought this is easy, straightforward to do, right? Why are they getting a Nobel Prize for this? But yeah, now that they have done it, now it looks very simple. But yeah, those days they were stuck with those nanojoule energy pulses, right? So that was the deal. Okay, now I want to go back to what we were discussing previously. And what we were discussing previously was characteristics of the laser. We said, okay, the one part of it is the output power characteristics, and we said output power, when you plot as a function of pump power, you have a certain amount of pump power that goes into creating gain in the medium, gain in the cavity to overcome the losses in the cavity, right. And so that is what we call as the threshold pump power. And you can also say that below threshold it's primarily spontaneous emission that's dominant, but above threshold you have a lot of these pump photons getting converted to signal photons. And so we were trying to figure out what is the slope efficiency for that, and then we went around and derived some expression for the slope efficiency. And then within that expression, we said we needed to optimize the partial reflection of your or the transmission of your output coupler, so that you can extract the optimum amount of energy. So we went through some math to figure that out, what has got to be that optimum transmission. Now that is on one side. The other side is we want to look at what are the spectral characteristics of your laser, okay. And to look at the spectral characteristics, now we are looking at it as function of laser frequency. We say, okay, the loss is at this level, right, and if your gain line shape is like this, then you basically say that you have all these longitudinal modes that are spaced what? C over 2 times NL, where L is the length of the cavity and N is the refractive index of the medium inside the cavity. So you have all these longitudinal modes in this laser, right. But of course, this picture is slightly flawed, okay. This is not typically what you see from your laser, okay. So what happens is, of course, your gain gets saturated, right, as you have all these photons that are oscillating in the cavity, and then it can create some issues, right. To track that, we have to consider two different types of material. One is called homogeneous broadened material and another is called inhomogeneous broadened material, okay. So, example for homogeneous broadened material is probably semiconductor material, right. So, gain in a semiconductors are like this, where when you look at the gain as a function of frequency, we said it's got a certain line shape, right. It's got a certain line shape, and when you saturate the gain medium, when you have a large number of signal photons inside the cavity, what happens is that line shape remains, but the overall gain actually saturates. So this is basically the effect of gain saturation in a homogeneously broadened medium, because when the gain saturates, it uniformly saturates across that entire medium. If it's a semiconductor, we're talking about something in the order of 100 microns, right? That is the typical size of the semiconductor, and the saturation is such that the photon density, you can say, is sort of uniformly spread around that region, and the saturation is uniform. So the entire gain spectrum comes down sort of in a uniform manner. Okay. So if you have, let's say, the case where your this is corresponding to alpha r, right? If your losses inside the cavity is at this line, then this is actually suggesting that, of course, in steady state, what can you say about the laser in steady state? What can you say about the gain of the laser in steady state? Gain should be equal to the loss, right? So if you say the whole line shape remains and the gain gets clamped at the loss line, what does it say? It basically says that only a single longitudinal mode can survive in the cavity. Okay. So that is what you expect as far as a homogeneously broadened, theoretically a homogeneously broadened medium should have only one longitudinal mode. Okay. But of course, when you talk about practical situations, the practical situations, if you have let's say one mode, one longitudinal mode existing within the cavity, let's say my cavity is like this, right? So if I say there is only one longitudinal mode happening within the cavity, basically it says that something like this, only one particular mode is there. So the reflected component will be like this. So that will be like there will be one standing wave pattern. Okay. But if you have one standing wave pattern, there are regions of high intensity and low intensity. Right? If it's a standing wave pattern, it corresponds to regions of high intensity and low intensity. At low intensity, your gain is not saturated. At high intensity, the gain is saturated. Right? So it cannot remain as one mode, because your gain is unsaturated in these regions, at these null regions, and it's saturated in the other regions. So then the gain actually grows in a nonlinear fashion. The gain available to you is more in this other region. So it tends to actually find some other mode where you can you can have that constructive interference criteria. So it doesn't remain in this mode, it starts oscillating in some other mode, some other neighboring mode, and some other neighboring mode, and so on. Right? So it actually jumps between all these modes. Do you understand? So your gain saturation typically should happen such that the line shape is maintained. So under that condition, the gain clamps at the loss line, and you have only one longitudinal mode oscillating, right? But one longitudinal mode corresponds to a standing wave pattern, and a standing wave pattern has got high and low intensity regions. High intensity regions are heavily saturated gain, so you don't get as much multiplication, whereas at low intensity regions you have more gain. So, you multiply more, and that means it is not low intensity anymore, it is going to high intensity, right. So, that means it is actually looking for some other mode which satisfies, which can fit within the cavity. So, it will be one of the other longitudinal modes that can fit into the cavity. So, it actually oscillates between different longitudinal modes in the cavity. Line shape overall remains the same. So, now you basically the overall line shape would have to change accordingly. So, if it is the steady state condition is that whatever mode that is oscillating has got to have gain equal to loss, but which mode satisfies that condition, it is actually changing as a function of time. So, if you are looking at a time average picture, it will feel as if all those modes are oscillating, because they are fluctuating at a fairly small time scale, in a microsecond time scale. Okay. So, it would seem like in a steady state, if you are doing a measurement over a millisecond, it seems like all those modes are oscillating simultaneously. Okay. But theoretically, the point is, without you, if you do not consider gain saturation, only one mode should oscillate in a homogeneously broadened system. There is a question back there. So, it takes away gain enough to overcome the loss. It gets clamped there. But for this picture, but for this gain saturation picture, where this is actually an effect called spatial hole burning. So, spatially it's burning a hole, meaning it's saturating some specific points along that gain medium. Yeah, what is the question? So, in this case you have, well, if you are talking about one longitudinal mode, that longitudinal mode corresponds to a standing wave pattern, and standing wave pattern essentially means you have clearly defined high and low intensity regions. So, the saturation level in these regions are different. So, that means it is always trying to go to some other mode where it can actually that can be supported by the cavity. So, it oscillates between different modes. If it is one mode, it corresponds to one specific intensity pattern. So, what we are saying is it corresponds to, this is high, low, high, low, high, low, high, low. So, in these regions where it is high, the gain is lower, right, and the other regions where it is low intensity, the gain is higher. So, it is actually trying to amplify those photons in those low intensity regions. Then that does not satisfy this particular mode condition, because what defines this mode is a specific standing wave pattern. That standing wave pattern essentially gets distorted by this gain saturation phenomena, right. So, specifically at the low intensity regions, the gain is higher. So, it tries to find some other mode where it can satisfy, it will be a slightly shifted mode. It's not the path length is fixed. Its path length is fixed. So, what all these longitudinal modes mean is that each one of those correspond to a standing wave pattern, but they are slightly different period. So, let's look at it like this. If I am looking at some mode like this, you know, when I look at that condition or the mode that satisfies a particular cavity, this mode number can be 6500, this mode number 6501, this mode number 6502. What does that mean? It has got 6500 fringes within that cavity, right? Now, if there is anything distorting that pattern, it will go into the neighboring pattern, which allows 6001 fringe or 6499 fringes, right? So it will distort and it will go to some neighboring modes. It will get into that, right? So that is what we are talking about. It's when you consider that it's that many, it corresponds to a wavelength, right? I randomly threw out a number 6500, but let's say your cavity length is 100 microns. If you have 1 micron wavelength, so 100 wavelengths would have to fit into that, right? So we are talking about, if it's 99 wavelengths fitting into that, that corresponds to a slightly higher wavelength than 1 micron, maybe 1.01 micron or something like that, right? So all these longitudinal modes are corresponding to that, right? Multiple modes are possible in a laser cavity. It's not like all of them are present. That's what we are trying to say here. Huh? It cannot be, because as technically standing wave essentially says that you have a high and low, right? So then we are talking about different levels of saturation, different levels of gain for different points in that cavity, right? So the lower gain or lower intensity or higher gain, they will multiply faster than the other guys. So then that is distorting the standing wave pattern. So it will tend to go to a neighboring pattern that fits. That too momentarily, because the saturation once again happens and all that, right? So that is what we are talking about. Well, things are much simpler, luckily, when we are considering inhomogeneous broadening. Inhomogeneous broadened systems are such that I don't have the same property everywhere, right? So some location has got this sort of gain spectrum, some other location has got this sort of, some other location has this sort of gain spectrum, and so on. So it's like multiple independent oscillators are present in this system, right? And in this, oscillation at 1 does not prohibit oscillation at, because the saturation levels are different, right? So I can have multiple modes that could be present within my cavity, right? Multiple independent modes that could be present within the cavity, as long as they independently satisfy the gain and loss criteria. Okay, so this is allowed. In the other case, if you say it's homogeneously broadened, it means homogeneously saturating, and if it's homogeneously saturating, theoretically only one mode can be oscillating, but then practically we see all these because of the spatial hole burning issues, we have all these other things happening. But here you could have independent oscillation, independent saturation of the medium. Example for this is neodymium glass. Okay, that is one good example. But even when we talk about erbium dope fibers or ytterbium dope fibers, they exhibit inhomogeneous broadening. Erbium, for example, you were experiencing this in your last experiment that you did. When you look at the gain as a function of frequency or wavelength in erbium, the gain spectrum would have looked something like this, right? And it's got a long tail here, somewhere over here. So the peak is at 1530 and it comes down rapidly beyond 1560, doesn't have much gain below 1520 nanometers, right? So with the erbium system, you have a certain portion around 1530, let's say, that is actually, that portion is homogeneously broadened, meaning all the oscillations around there, they saturate uniformly. But when you consider the entire spectrum, especially at the peripheries of the spectrum, they correspond to inhomogeneous broadening, meaning their saturation is independent. Okay. So this is the experiment you did. In one case, in your ring cavity, so you had basically a erbium dope fiber amplifier, right, which is pumped, counter pumped with some with pump at 980 nanometers. But what you did was you took that and you looped it back. So there is no external signal fed in, it's all within, I mean, whatever was the output of the erbium dope fiber, you fed it back as the input, right? That's how you made a ring laser. And what you did was, you put an element over here, you sent it through a circulator, which led to a element called a fiber Bragg grating, right? You put a fiber Bragg grating into this, so that light actually goes through the fiber Bragg grating and comes back. And the fiber Bragg grating, what it did was, it was reflecting only at one wavelength. Okay, all the other wavelengths, it was providing very high loss. So my loss line now, it looked like this. This is my loss of the cavity which incorporates the fiber Bragg grating, right? And this made sure that only at one wavelength you have gain overcoming the loss, right? And only at that wavelength you were having oscillation. So if the grating was highly reflecting at 1550 nanometers, right, that is where it is highly reflecting. 1550 nanometers is the oscillation wavelength you saw, because all other wavelengths are just escaping through this fiber Bragg grating. They are not recirculating in the cavity. FBG is a filter, it is a reflection type filter. It reflects only one particular wavelength, all other wavelengths, it is very high loss. So you do not have enough gain to overcome the loss, okay. And because of that, you are able to get oscillation only at one wavelength. You locked your output to only one wavelength, right. That is the laser you built, okay. Now you built one more laser. You remember what you did? What was that laser about? I still had the same erbium gain spectrum, right, with a peak at 1530 nanometers. But in this, what did I do? Instead of a FBG, instead of a circulator and FBG, I introduced a variable optical attenuator. So what was I doing in that case? By changing the attenuation in the cavity, I was actually changing your alpha R, right, through the VOA, variable optical attenuator, right. So now in this case what happens? You have essentially, when you consider the highest or the lowest loss case, the lowest loss case, it can oscillate anywhere, but if we oscillate around 1530, it's getting severely saturated, and on top of that at 1530 you also have absorption happening. Your absorption cross section at 1530 is higher than what it is at longer wavelengths, okay. So lot of those wavelengths were getting reabsorbed inside that. So with the result that at this level you are seeing some oscillation over here, right. And then as you increased your loss in the cavity, you are moving to this point. As you increase the loss further, your loss and gain point was meeting at some other wavelength, right, at a shorter wavelength. And when you increase the loss further, you got to this point, even shorter wavelength. Because with very high loss, only the peak of the gain can overcome the loss. The peak of that gain spectrum can overcome the loss, and because of that your oscillation was actually happening at a much at a lower, at a shorter wavelength. So you saw as a function of if I were to plot the output wavelength as a function of attenuation, as I increase my attenuation, the output wavelength becomes shorter, right. Did you observe that? As you increase your attenuation in the cavity, your output wavelength became shorter, okay. So these are the considerations when you think about the spectrum of the output spectrum of your laser, right. So the output spectrum typically is determined by where the gain meets the loss. That's right, yeah, it has got to be a longitudinal mode. There is no way to get around that. So it has got to be a longitudinal mode around that particular frequency. Yes, it has to line up with one of the possible longitudinal modes in the cavity. Only those will satisfy the phase matching condition, okay. So what we will do in the next lecture is actually jump a little bit. I think we have talked about enough rare earth doped systems, this dilute gas type of systems. Let's actually jump into semiconductors and let's start understanding how these holes and electrons, how they interact with, how they recombine to generate photons, how photons can be absorbed in the material to generate electron hole pairs. So one is the source and the other is the detector. So how does all those physics work out, and what are the corresponding photonics issues related to that? We will discuss that starting tomorrow. Okay. Thank you.